All right, so for 1.6 now, we'll take a look at what are called other types of equations. The main three I want to talk about in this section are polynomial equations of higher order, or higher degree. Like we see here, a fourth degree polynomial and a third degree polynomial, so we'll take a look at that in a second. Also radical equations as next on the list, and then finally absolute value equations. There are other types of equations that we may look at, but those are the main three I want to focus on anyways. So for polynomial equations first, I say that a polynomial equation will look something like this. You want it to be a polynomial equals 0. Think of what we had for quadratic equations. We moved everything on one side so the 0 was on the other. And that was a quadratic equation. Good. So I say three things here. The main methods we'll be using to solve are solved by factoring and zero factor property methods. Those are basically what we're going to be doing. But there are kind of two different types. One, we may need to factor by grouping, so keep that in mind if it's a kind of unusual case, which we'll see after. And then we're going to look at for what are called polynomials in quadratic form. So these first two are a little more straightforward, and the next examples we'll look at after these two will involve these last two types, by grouping and quadratic form. But let's, in any event, let's carry on and move on with these two. So here we're just going to factor. So what do they have in common? Well, notice we can divide each of these by 6, and they both have x squared. So we pull out 6x squared, what are we left with? The first term will give us x squared if you factor out 6x squared. This will be negative 9 now. Right? 54 divided by 6 is 9. The negative is still there, and it loses its x squared. Great. Can we keep factoring? Yes, we can keep factoring. How? This is a difference of squares. So if you keep factoring, we get x squared, 6x squared, outside of x minus 3 times x plus 3 because we have a difference of squares, and that's how we factor those. Now we can use the zero factor property. And what does the zero factor property say? Well, it basically says that we can set each of the factors equal to 0 if we have a product equals 0, and we do. That's why we want 0 to be on one side and then factor the non-zero side, essentially. So when we set this equal to 0, all you'll get is x equals 0. You can see divide by 6, x squared is 0, square root of 0 is still 0. So for the first factor, we get x is equal to 0 as the solution. Here, we know how to do this. Change sign, opposite sign. We get positive 3. Same thing here. We get negative 3. So these are our three solutions. You can check by plugging them into the original equation, but yeah, they work. Here, very similarly, they all have something in common. They have 5 in common, and they each have an x that you can pull out. So we pull 5x on the outside. This loses 5x, so it's x squared. 30 divided by 5 is 6, loses an x. 45 divided by 5 is 9, loses an x. And can we factor this? We can. And if you remember completing the square, half of 6 squared is 9. So that means this whole thing is actually a square. So we can factor this as basically x plus 3 times x plus 3. So really it's x plus 3 quantity squared. Now finally applying the zero factor property, when 5x is 0, we get x is equal to 0 as a solution. Good. When x plus 3 is equal to 0, we get negative 3 as a solution. And remember, since it's squared, technically negative 3 comes out as a solution twice, meaning this would have multiplicity 2. Just keep that in mind. I'm not going to write that out, but that's just something you should probably keep in mind. And that was it for these problems, and now we're going to take a look at some other types of polynomial equations that will involve these last two criteria I was talking about earlier. Let's see that right now. Okay, so these are two different types of polynomial equations. The first type can be factored. Of course, we need to write it in the form we like, so the 0 is on one side and everything else is on the other. So I'm going to add 3 from the right to the left. Right? And now what can we do? We can factor by what is called grouping. So we can factor each of these pairs of terms one at a time. So notice the first two have x squared in common. Pull that out. And these two don't appear to have anything in common, but notice if we want this to look like x minus 3, if we pull out the negative that's in front of this x, we'll get x minus 3, which sounds funny, but if you were to distribute the negative back in, you get negative x plus 3 indeed. So this is definitely true. Also, since both of these have an x minus 3 in common, and this is a negative 1 times x minus 3, we can factor x minus 3 as a common pair, or a common factor, I guess you could say, outside, and what we'll have left are these two, namely x squared minus 1. Perfect. We can continue to factor, of course, because x squared minus 1 is a difference of squares. So completely factored, it's x minus 3 times x minus 1 times x plus 1. And now using the zero factor property, x is equal to positive 3, positive 1, and negative 1. Fantastic. Moving on to the next one. This is a little different. This is what is called basically quadratic form. It's in quadratic form. We'll see another example of quadratic form in a second, but first let's handle this one. What I'm going to notice is that this is x squared squared. Yeah, I'll just leave it like that right now. So basically, if we let u equal to x squared, then we get the following. We get u squared minus 16 is equal to 0. We can factor this in terms of u, difference of squares. It's u minus 4 times u plus 4. And then we can, well, set each of these equal to 0 using the zero factor property. Using the zero factor property, we get either u is equal to positive 4 or negative 4. Okay? But what was u? U was x squared. So if we replace u with x squared, we end up getting x squared is equal to positive 4 or negative 4. Now there's two cases. When x squared is equal to positive 4, let me write that over here. If you square root both sides, you get x is equal to plus or minus the square root of 4, which is plus or minus 2. That's great. In the other event, when x squared is equal to negative 4, when you square root both sides, you get x squared is equal to, well, the square root of x squared, x, is equal to plus or minus the square root of negative 4. So here this was plus or minus the square root of 4, which was 2. Square rooting x squared, they cancel out. Here, square rooting x squared, so I guess I'll write it out like this. Cancels the squared, leaves you with x. The square root of 4 is 2. Since it's negative 4, remember what we saw from 1.5, this is 2i. So it's not a real solution. So if you want to look at only real solutions, these are the only ones. But if you want to look at all solutions and you don't care about real or complex solutions, then we actually have four answers, plus or minus 2 and plus or minus 2i. And now we'll take a look at one more example of quadratic form right now. All right, so back to another type of polynomial equation that is of quadratic form. And I'm missing a square here. Sorry about that. And yes, let's again let u equal x squared. It's less obvious here. But again, if you recognize the fact that x to the fourth is really x squared squared because of multiplying the powers, that exponent property, then this polynomial equation turns into u squared minus 5u plus 4. This is why it's called quadratic form, because with a simple substitution, you can write it as a quadratic equation. It's like a quadratic equation in disguise, really, with a substitution. This can now be factored as u minus 4 times u minus 1. Remember, two numbers and multiply to 4 and add to negative 5. Good. And now using the zero factor property, we get u is equal to either positive 4 or positive 1. But remember, what is u? U is really x squared. So x squared is either positive 4 or x squared is either positive 1. Since they're both positive, we won't have any complex solutions like we did in the last problem, but we still get something after square rooting. Remember, after square rooting, we get x is equal to plus or minus the square root of 4, which is 2. Here we get plus or minus the square root of 1, which is negative 1. And these are the four solutions to this original polynomial equation. Okay. Now we're going to move on to talk about something a little different type of equation. The second type I mentioned were radical equations. Radical equations are equations that can be written as a radical of an expression is equal to either a number or even possibly another expression. So this number I'm writing, let me just say may be an expression. There are a few keynotes here. First, we need to square root both sides when the radical is isolated. So let me just say radical must be isolated. Radical is, let me just say, isolated. So get the radical by itself first, then we can square both sides. I'm just going to say this. We're not going to do an example of it because it's a little too specific. But this index could possibly be cube root or fourth root or fifth root or seventh root, whatever the case may be. And in that case, you wouldn't square both sides, but you would take both sides to the power of that index. So if it was a cube root, you would cube root both sides, cubing both sides, not cube root both sides, I'm sorry, cube both sides. When you cube a cube root, they cancel just like squaring the square root cancels it out. Again, we're not going to do any examples involving those, but that's kind of technical. You can definitely do that. Also, I say FOIL when necessary. That really only takes into effect when this number is an expression. When you score an expression, you have to FOIL it out, so be aware of that. And here you must check your solutions. And we'll see why when basically when we get more than one solution, but it could possibly happen only when we have one solution. Just long story short, check your solutions when you have any radical equations. So let's see why. So here the radical is isolated, so we're going to just square both sides of the equation. And what we'll get is, well, the radical and square cancel, so we get 2 minus x is equal to 5 squared, 25. We can add x to both sides and subtract 25 to both sides simultaneously. So let me write that. Plus x to this side and subtract 25 to this side. So we get 20 minus 25 is negative 23 is equal to x. Great. This may sound a little weird to you because you may think, oh, we have a negative inside the radical. Not the case. And let me just show you because I said we have to check. So might as well check anyways. If we check, we're plugging in x equals negative 23 into our original equation. Our original equation is this. The square root of 2 minus x, which is negative 23, and hopefully this will be equal to 5. Hopefully, that's why I'm writing question mark, because we're not sure. Now notice, double negative is positive, so this is the square root of 2 plus 23, which is 25. That is indeed 5, so 5 is equal to 5, and it checks out. And now we're going to see another example of this. But to see another example, well, we're going to have to see certain cases. The next case I think we're going to want to look at is when we don't have a number on the other side, but an expression. And let's see what happens right now. All right, so I mentioned earlier we won't really be taking a look at examples that involve cube roots, but I kind of lied. We're going to take a look at one right now. Before we move on to this. So let's see what happens. First we need to isolate the radical, so very similar story. So let's subtract 4 to both sides first. So we get cube root of 2x minus 9 is equal to negative 4. So now remember, to get rid of the radical, you need to take both sides to the power of the index. And in this case, the index is 3, so we're going to take both sides to the third. Okay. Here, the root and the power cancel out, so we just get 2x minus 9. Over here, negative 4 to the third is negative 64. 4 times 4 times 4 is 64. Triple negative is negative. Good. So now add 9 to both sides. Okay. Let's see, what's negative 64 plus 9? That's negative 55, I believe. Right? So now dividing by 2, this leaves us with x is equal to negative 55 over 2. And something I kind of want to say here is that you don't actually have to check your solution when there is an odd root in the original equation. I want to check this anyways, so let me check it over here in some space I have here. So let's see, so to check this, we're going to let x equals negative 55 over 2. So plugging this in, we get 4 plus the cube root of 2 times negative 55 over 2 minus 9 is equal to 0. Hopefully equal to 0. We don't know. Okay, the 2's cancel, so we get negative 55. Negative 55 minus 9 is indeed negative 64. The cube root of negative 64 is negative 4. Now I'm kind of going all over the place. Let me just fill out some of these details here. There we go. The cube root of negative 64 is negative 4, and the reason being there is because when you cube negative 4, we get negative 64 like we saw earlier. And notice 4 minus 4 is indeed 0, so it is a solution. It checks out. Great. Now this is the one I kept hyping up earlier, where you have not a number on the other side, but an expression actually. The radical is already isolated, so that's fine. Let's just square both sides, because this is a square root. So if you like, there's always an imaginary 2 under a square root. If there's a number, then it's that root. So like here, it's a cube root because it's 3, third root. Third root, cube root. Second root is square root. You don't need the 2. So very often for radicals with a 2 index, we don't write the 2. It's just square root. Good. So now these cancel out on the left, so we're left with x plus 8. On the right, what do we have to do? We have to FOIL. So if we FOIL this out, it's going to be the first one squared, the product times 2, 2x times 2 is 4x, and then the last one squared is x squared. What do we have left here now is a quadratic equation. Can we solve it? Yes, we can. How do we solve it? Move everything to one side so the zero's on the other, and then factor the non-zero side. So I'm going to subtract all of the stuff on the left to the right. So minus x minus 8. These cancel. We get 0 on the left is equal to, let me write this in order, x squared plus 3x minus 4. This can definitely be factored. If we factor the non-zero side, the two numbers that multiply to 4 and add to 3, I think, are 4 and 1. If you change our signs as positive 4 and negative 1 like this, positive 4 and negative 1 will indeed multiply to negative 4, and they'll also add to positive 3. So perfect. Now applying the zero factor property, like we've been seeing, we get x is equal to negative 4 or positive 1. I would box this, but what did I say about these kinds of equations? You have to check. I'm going to check them a little quickly, but let's see. So when checking x is equal to negative 4 to the original equation, we get the square root of negative 4 plus 8 is hopefully equal to 2 plus negative 4. So we'll check that in a second. When plugging in x is equal to 1, the other supposed solution, we get the square root of 1 plus 8, good, is supposedly equal to 2 plus 1. Great. So now for this one, we get negative 4 plus 8 is 4 on the left. On the right, we get negative 2. The square root of 4 is 2. And we get 2 is equal to negative 2, which is, of course, bogus. That's not true. Okay. What happens here, we get 1 plus 8 is 9. The square root of 9 is 3. So we get on the left. On the right, we get 3 as well. 3 is equal to 3. Perfect. So as it turns out, x equals 1 is actually a true solution, but x equals negative 4 is actually not a true solution. X equals negative 4 ended up being an extraneous solution, actually. It was extraneous. Because even though we did the algebra correctly, well, it didn't check out. It wasn't an actual solution. So all in all, the real solution, the real only solution is x is equal to positive 1. Why does this happen? It's something you can think about for a little bit if you like. I don't want to think about it too much. I don't want you to think about it too much, because then it gets a little funny, and then you'll get confused maybe. But let me just say this. When we're squaring both sides, this is not a reversible process. When you square both sides of an equation, remember, square rooting, you get a plus or minus. And that's what happens here. If there was a plus or minus in front of this radical, squaring both sides would still give us x plus 8. So let me just rephrase. If it was a negative radical here, then squaring a negative would give you positive x plus 8 anyways. But notice, if there was a negative in front of the radical, then this would be negative 2 is equal to negative 2, and it would work. But on the other hand, this wouldn't, because it would be negative 3 is equal to positive 3. So that's the reason why we get these two situations. And that's also the reason why you have to check your solutions for radical equations. So that's the last I want to say about radical equations, and now let's move on to absolute value equations, and we'll see that right now. Okay, so actually before we move on to absolute value equations, I did mention at the very beginning of this video that we may possibly look at other types, and the only other real type I want to focus on besides polynomial, radical, and absolute value equations is this type, where it's a rational equation involving rational functions basically, or rational expressions I should say, that involve denominators of x involving x, so they're nonlinear. Okay, right, so here this will actually turn into a quadratic equation after the fact. So remember how we solve these things. We first find an LCD, kind of like how we did in 1.2, and it is x times x plus 1. Multiplying through by x times x plus 1 will actually cancel out all denominators. So we're going to treat each of these terms as passing through this filter, treating the LCD as a filter. When you multiply everything by the LCD, the denominators will be canceled out or filtered out if you like. Good. So when you multiply 1 over x by this, the x's cancel, so it's just 1 times whatever didn't cancel, x plus 1, minus 1 times whatever didn't cancel with this one, x plus 1 cancel, x doesn't, so times x. With 3, there's no denominator to cancel, so 3 gets all of them actually, times x plus 1. Perfect. So now we'll simplify this a little bit. This is, of course, just x plus 1 minus x. These distribute, and we get 3x squared plus 3x. Notice here the x's actually cancel out. And what now? Well, now I guess we can subtract 1 to the other side and solve from there. Do I want to do it that way? I guess let's just do it that way. So we subtract 1 to the other side. We get 0 is equal to 3x squared plus 3x minus 1. This, as it turns out, is not factorable, so I'm just going to use quadratic formula. It's a quadratic equation after all. Just remember, a is 3, b is 3, and c is negative 1 in this case. So it's a negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Okay. I'm going to be a little quick about this, but we get negative 3 plus or minus the square root of, let's see, 3 squared is 9, double negative is positive, 4 times 3 times 1 ends up being 12. 4 plus 12, by the way, is 21, all over 6. So we get negative 3 plus or minus radical 21 all over 6. These are our solutions. There's 2 of them. And yes, technically you have to check these because you can possibly have 0 denominators. Notice we would only have a 0 denominator in this case when this denominator is equal to 0 or when this denominator is equal to 0. Since this solution is neither of these two, they're both okay solutions actually. So there's not too much checking to do. So now finally on to absolute value equations. I'm only going to go over this one example here. And I say the following. An absolute value equation is an equation of the form absolute value of an expression is equal to a number. And I say the following key notes. We want to set the expression equal to plus or minus that number. Which makes sense because if you remember, absolute value of a number is just the number itself without the sign. So if the inside is positive 3 or even negative 3, then that means the absolute value will just be the number without the sign, which is just 3. That's what absolute value means, really. Okay, so going backwards, if we have the absolute value of something is equal to a number, then that means that number must be, well, that something must be plus or minus that number. So like if this was x, the absolute value of what is 3? Well, positive and negative 3 both work because positive 3 absolute value of that is 3. Absolute value of negative 3 is also 3. So think of that. Here you must check the solution basically because of this last reason. When the number is negative, then there's no solution. This should make a lot of sense because what we kept saying here is the absolute value is the number without the sign. In other words, it is always positive. Absolute values are never negative, they're always positive and only positive. So if you have an equation, an absolute value equation where the absolute value is equal to a negative number, it's a bogus equation. It has no solutions. That's all this is saying. So let's see this example here. We're going to set the inside 5x minus 3 equal to plus or minus 12, according to what I said here. Okay, we're going to add 3 to the other side to get 5x by itself. Then we're going to divide both sides by 5. And we are finally going to get x is equal to 3 plus 12 is 15 over 5, or minus 3 minus 12. 3 minus 12 is negative 9, so it's negative 9 over 5. 15 over 5 is 3. So we get simplified, x is either 3 or negative 9 over 5. And you can check these. I'm not going to check them, but you can check them. And you'll indeed get this. And that ends the discussion for 1.6. And I'll see you in the next video for 1.7. Thanks for watching. See you then.